All right, so this next subunit is going to be on nuclear power, its benefits and its consequences. This may have to be split up into two videos. We'll see how it goes. All right, so the objectives for this subunit are to compare and contrast the process of nuclear fusion and nuclear fission, describe the uses of nuclear energy, and examine the possible consequences of using nuclear energy. So let's start off with what is nuclear energy. Nuclear energy, basically, it's just there's this immense amount of energy inside the nucleus of an atom. It's very small and very dense. And to be able to have that very small, very dense thing happen, you need a whole bunch of energy holding it together to make the bonds or to split it apart to make it be able to form other bonds with different molecules. So it's very dense, it's very small. Nuclear energy is contained in the bonds holding the nucleus together, so that's where the neutrons and the protons are, the most dense particles inside of an atom. They can be used in two different ways to get nuclear energy. You can do this by you can release energy by breaking the bonds, and that's called fission. So when you split the nucleus apart, you split those neutrons and protons apart, that's called fission. That's what we currently use for nuclear energy. And it can also be released by creating bonds between the atoms. So you're creating these bonds. You're making two very small, very dense particles, well, not just two, but many, come together and form an atom, essentially. And that's what fusion is. So fission is the breaking, fusion is the coming together of these atoms, or bonds anyway. And then just to remember, this is really basic. Energy can neither be created nor destroyed, and that's the first law of thermodynamics. So you can't just create energy. You're using the energy that's around us in this world, and this nuclear energy is it's potential everywhere, all around you. There's atoms floating around. You're releasing atoms. You're taking in atoms every second of every day. So this isn't like energy that we're creating. We're just harvesting it from the potential around us. So that's just something to remember. This goes for mass as well. So mass can neither be created nor destroyed. Essentially, that's just like a play on the energy. So mass is essentially energy. It's just the way that it is formed, the way that these atoms are formed creates a mass. So there's all these atoms are floating around us no matter what. If they form together, they create a human being, something like that. That's going to be mass that we can easily quantify, but we can always quantify mass. We know how much every atom weighs, every element, all that stuff. We can weigh the air if we really want to. Okay, so let's get to uses of nuclear energy. So a good use of nuclear energy is it's going to be able to generate a lot of electricity. It's generally clean electricity as well, so that's pretty good. Another use are bombs. So we've got the atomic bomb, which is a fission reaction. And so remember, fission is the separating of an atom. And then a good example of that is going to be the Bikini Atoll bomb. And I'll get into that in the next couple slides here. And then we've also got the hydrogen bomb, which is a fusion reaction, but it's started off by a fission reaction. So the hydrogen bomb essentially is a fission reaction. So we split up an atom, have a fission bomb go off that causes so much energy to be released that we have these atoms forming together, and that creates the hydrogen bomb. So it's a fission bomb, a fission explosion that creates the fusion reaction. So that's how hydrogen bombs happen. And a good example of that is the Russian Tsar Bomba. And this was in, I think, the 70s or 80s. But it was the biggest bomb ever blown up. It was an equivalent to all the explosives used in World War II put together times 10. So that's quite a bit. It sent a shockwave that went around the world 3 times. So this bomb was extremely powerful, and it has the potential to, cause like the world to be devastated. Just one bomb. I think it was 50 kilotons. We'll get into that. But then some bad things. Bombs, for sure, are bad things. Nuclear bombs are never good. No matter what way you look at them, all they do is destroy. They really leave places in bad shape, disrepair. So nuclear bombs are a no-no. They're super bad. We're in kind of an era where we're thinking about using nuclear weapons again, but I'll give you some examples of why we probably should not use them. And then another bad thing is going to be like nuclear meltdowns at power plants. So Chernobyl, 3 Mile Island, Fukushima, they happen. And essentially they're just creating one big nuclear bomb, not quite as big as the potential we have for like a hydrogen bomb, but it's still very devastating. So here's just, you're going to want to pause this and look at this. This is giving you all the examples of the differences between nuclear fission and nuclear fusion. So fission is the splitting of an atom into smaller ones, and then fusion is the fusing of 2 or more atoms into one atom. So essentially, fission cannot happen normally in nature. We created that. Albert Einstein basically created that. And then fusion happens in stars. So on our sun, we have fusion reactions going on all the time, and that's how we get our energy. So we've got some byproducts. Fission produces many highly radioactive particles. Fusion has hardly any radioactive particles. The only time it does is if you have to use a fission trigger to create this fusion reaction, like I was telling you about. Some conditions. Fission's pretty easy. You just need to have a bunch of energy slamming into a small particle, and then that will explode that and create a bunch more energy. Fusion needs a whole lot of energy. So the problem with fusion is that we don't have many good ways other than creating fission reactions to start the fusion reaction. So you need a whole lot of energy, and the amount of energy that you get back is about 3 to 4 times more than fission. So it's a crazy amount, but it's just hard to get it started. So extremely high energy is required to bring 2 or more protons close enough that nuclear forces overcome their electrostatic repulsion. So they're constantly trying to push each other away. So you need a whole lot of energy to bring them together. So that's why fission is easier. So energy released by fission is 1,000,000 times greater than that of chemical reactions, but it's still 3 to 4 times less than fusion. So if you can imagine that, it's 1,000,000 times greater than chemical reactions, but then multiply that by 4, and that's how much fusion energy gives us. So this is the future right here, is fusion energy. And then we've got bombs. So fission bombs are the atomic bombs, and then fusion bombs are hydrogen bombs. So they generally use a fission reaction to trigger the hydrogen bomb fusion reaction. All right, and then here is just how much energy is produced by fusion versus fission. So this is millions of electron voltages, something like that. This is a unit of energy, MeV, and they calculate it out to get certain units of energy, and this is 676 units of energy versus 176 units of energy for fission. So fusion has quite a bit more units of energy. The only thing is that you need to use a lot more energy. You need to put a lot more energy into the system to get a lot more energy out. So that's what makes fusion hard. So here's the Bikini Atoll that I was telling you about. All these trees have stripes on them because they're trying to figure out how much water is going to come up, like how big of a wave is this explosion going to produce. And so there's a bunch of boats out here, and these boats are empty. They're just trying to figure out, how close can a boat get to an atomic bomb before it gets destroyed. And all of these boats were unusable. So interesting thing about this Bikini Atoll is the residents of this island and the Bikini Atoll were forced to move to a separate island, and they were told that there would be a small explosion and they would be able to move back to their homes. Well, there was a large explosion. It completely destroyed the island, and all of these people were left without homes, and then all of the area around here was contaminated with nuclear waste. So pretty much everybody who lived in this area was displaced from their homes just because we wanted to test a nuclear bomb to kill people with. And then here's Sarbama. And right here, this is the upper limits of the stratosphere. So as you can see, this bomb's mushroom cloud went out into space. So this was like the most amazing explosion that was ever occurred on Earth. And this shockwave went around the world 3 whole times. So this is something we don't want. There's plenty of hydrogen bombs out there as well, so that's something to be a little worried about. And then here you go, 50 megaton SAR bomb. This is how high its plume went. Okay, so here's Mount Everest. Here's where you fly 30,000 feet. And then here are the 2 atomic bombs we dropped in World War II that completely devastated Japan. So imagine one of these bad boys anywhere on Earth. It's going to devastate the whole Earth, basically, if you put this on a metropolis area. So, think about that. Nuclear bombs are not good. Here's 3 Mile Island. This is just an example of a plant that had a partial leak and almost had a meltdown, but they were able to stop that. But that leak still emanated radioactive material all throughout this area. This whole, these rivers here had to be decontaminated. It took years to make this whole area kind of get reclaimed again, and that was just a leak. So here's Chernobyl. This was a full meltdown. You can see right here, it just exploded. And then this is the nuclear effect of Chernobyl's nuclear meltdown. So this was a full meltdown. And this is, it goes all the way into Spain, the nuclear radiation from this meltdown. So they weren't super careful with their procedures. Their core rods got too hot. It caused a meltdown, which caused an explosion. And it was essentially just a nuclear bomb going off. And this is the whole area that got hit with RADS, basically, radiation. Here's Fukushima. This happened recently. You guys might remember this. There was a tsunami that broke into this nuclear power center. The rods they just got hit with a bunch of water. It caused a partial meltdown. And then there was a small explosion. And they're still dealing with contaminants and cleanup there as well. And then here is a 10-day fallout map, or 30-day, fallout map from Japan. So here's where it started. And then after 3 days, we had 3,000 RADs just going out into the ocean here. And then by 30 days, Colorado is getting hit with 750 RADs. So that's radiation that you previously were not exposed to, but got exposed to because of that meltdown. And then here's how a fission power plant works. So we get water in from a source. That water is condensed. That's not super necessary for the beginning process, but the water comes in, it goes through this little turbine, it gets heated up by these control rods. So this is uranium. It's getting really, really hot, and it's heating this water up. And so this water is going through, it's spinning this little cycle here. It's kind of creating a cycle of heating up and control. This is going to control the rods as well, the water, so it's not going to get too hot. And then that steam, after it gets heated up, steam is going to go up through this pipe. It's going to spin a turbine. That turbine is going to go to a generator, which converts it into electricity, and that goes straight into the power lines. Then that steam gets condensed, and at this point it's very hot, so it gets shot back out into the ecosystem, which isn't so great because that's going to affect aquatic life. Hotter water changes the physiology of many aquatic creatures, so that's not a very good thing. But then they're just continuously bringing in cold water to get heated up, push it through this turbine as steam, and then condense it back. So, really the only bad thing that comes of this is if we have a nuclear meltdown, and because the water that goes back out is a lot hotter than natural temperatures in that area. So, generally it's a pretty good thing. Okay, so we're going to stop here and we'll get into environmental consequences and finish up this subunit.